Welcome, everybody. I'm actually impressed. We have a bigger fraction of people here than I expected. This is good. So today I'm going to talk about distributed file systems ultimately, but I want to finish up a few topics from last time. If you remember, we talked about two-phase commit, which is very important in database area. And basically, two-phase commit could be motivated by saying we can't actually solve the general's paradox, which is having two parties who can only communicate over unreliable messaging agree on an exact time and then do something at an exact time. So it turns out you can't do that. But what you can do is kind of the next best thing, which is get a bunch of distributed parties to agree to actually do something for sure at some point in the future. Okay? And it's a form of distributed transaction. And so two-phase commit does what we need. It uses a log that's persistent at each one of the distributed machines to help out, because the notion is that one of the reasons you might not be able to do something immediately is you crash right away. So at every step, it's very careful, the two-phase commit protocols are very careful to record enough information in your local log that it doesn't matter who crashes when, but they can always come up, look in the log, and pick up where they left off, so that we atomically decide either that everybody will eventually do something or nobody will do something. There's never a some people do something and some don't. Okay? And there's two phases, which I talked about last time, the prepare and commit phase. That's why it's a two-phase commit. So the prepare phase basically gets everybody to agree that they are going to do something, and then the commit phase is only embarked upon after the leader of this protocol decides that everybody has agreed, and then they say, go ahead. Okay? And the log helps complete the process even when something falls through. So are there any questions? Yeah.
Just conceptually, if we didn't have to worry about crashing and that kind of thing, right? So the log just represents the state of
Yeah.
The whole two-phase.
Right. So think of this as the log is the distributed state of the protocol. And the machines are kind of, they're just there to carry out the protocol. And by having the log, what's cool is the machines now can crash and come back up and crash, but the protocol survives. And so it's about a stable protocol independent of what the machines are doing. So any other questions on two-phase commit? Yeah?
What happens if the very last commit doesn't get transferred?
If the very last...
Like the very, very last act doesn't take it.
So the nice thing about... So from who? From some participant says,
Doing all this preparation,
right.
running things logs back and forth, making sure that everyone knows what's going on, and the very last thing doesn't get there.
Yeah, so you're talking... So let me make sure I understand your question. Are you talking in the prepare phase? So think of it this way. So the leader says, I'd like to do this. And everybody who agrees sort of records I agree in their log and sends back a message saying I'm agreeing. If any of those messages are lost, the leader can ask again and get retransmitted until it actually has something from somebody. And then if not everybody agrees, then the leader can send out abort and they'll stop. Or if it gets agrees from everybody, then it can send out go ahead. And the go ahead message will be something that the folks that have agreed will satisfy because they've got in their log that they've agreed. And so every one of these phases here, kind of you can crash at any point, and you still have this one invariant, which is that either everybody does it or nobody does it. That's the. They don't get the go. Well, no. What happens is there isn't even a "Are you sure?" It's a go ahead, and and they will act that they went ahead, and so the leader knows that they didn't get it, so they can keep going until they said okay. So there's enough state in here to do retransmission until the leader knows that everything's happened. Okay, good. Any other questions? So, so why think about this in general? So this is sort of, I closed with this idea of distributed decision making. And one big reason is fault tolerance. It'd be nice if we could have a set of things helping us with a protocol, and even if individual pieces crash, we end up with a stable result. That's kind of nice. And it's basically a group of machines can come to a decision even if one or more of them fail during the process. Now, depending on how complicated you get, most protocols talk about fail stop, which is when somebody actually crashes, they crash in a clean way. If you let them crash in a dirty way where they might send out arbitrary garbage as they're crashing, these protocols get a lot more difficult. And at that point, in fact, we want to go to a Byzantine protocol like I'll describe in the next slide here. And after the decision's made, multiple people know about it. So it's hard to destroy a decision once it's really been made. So this is kind of a nice thing. Two-phase commit has this blocking property, which I mentioned last time. I won't go through it, but basically you can have a situation where somebody who crashes and takes a long time to come up can hold everybody up, because the protocol has to work in lockstep. You know, you first do this, then you do this, then you do this, and you can actually end up with somebody who already said they're ready to commit, and they're waiting on the leader because the leader crashed, and they can't do anything. They can't go on to the next step. They're just stuck until the leader comes up and says go. So there's a more fault-tolerant version called three-phase commit, where you add an extra phase in there, and there's a way to basically deal with somebody who isn't coming back up at all. Okay. Now, what none of these protocols deal with is maliciousness, and that's the last sort of topic on distributed decision-making I want to talk about. Let me describe what maliciousness is. Hopefully you kind of know in general, but from this standpoint, what we're talking about is we're talking about a participant in a distributed decision-making process that does whatever necessary to fool the protocol into doing the wrong thing. Okay, so what we allow a malicious node to do is a malicious node can say one thing at one time and something completely different at another time. They can watch the timing of protocols and zoom a message in at exactly the wrong time to cause it to screw up. They can fake data. They can say they'll do something and not do it. I mean, there's a lot of ways to be malicious. And what we'd like is a protocol that's basically resilient no matter what is happening with the malicious nodes. Now, as you can imagine, you can't build a protocol that can deal with all nodes being malicious. Okay, if every node is broken, you're basically hosed. Okay, and so the question about protocols that deal with maliciousness is what fraction of them can you tolerate being malicious? Okay? All right, so today I want to finish this discussion, and then we're going to move on to some distributed system issues like remote procedure calls, and we'll finish up with distributed file systems. So that's our goal for today. So, the Byzantine generals problem. How many people have heard of this before? Okay, a few of you. Now, what I posted up on for reading on the website, the original Byzantine generals paper, which is kind of fun because you actually see where it came from and so on. And it's basically a discussion of a particular scenario which is couched in kind of a war scenario, but it turns out it's very useful from distributed decision making. And it sort of goes as follows. There's n players in this game. One of them's a general, okay, and n minus 1 lieutenants, okay, and some of them are malicious, okay. Now, clearly the one with the black beard has to be malicious, or maybe, I don't know, these guys look the same, who knows. Maybe it's really this guy in disguise, who knows. But the question is, if they're insane or malicious, how many of these can you tolerate before we're toast? Okay? And so let's look at a scenario here. So the general says attack. And the problem is that none of the lieutenants can follow the order right away because they have to assume the general could be the insane one. Okay? So what the lieutenants are going to have to do is talk amongst themselves and make a decision about what they should do. And basically this game has two major constraints that we want to satisfy. Okay? The first one basically says that all loyal lieutenants obey the same order. So that's the first constraint. So whatever happens, all of the loyal lieutenants, or the ones who aren't insane, all do the same thing. Okay? And then secondly, if the general isn't insane, the lieutenants who are sane also obey the general. Okay, now I'm showing you a scenario here where the general said attack. Yeah, go ahead.
Well, I'm just kind of confused about what being sane versus insane would mean for the general. Couldn't he just, a sane general,
So an insane general would tell his lieutenants to do different things. Okay, in this particular scenario. Now, here is a case, here's the malicious guy. And if you notice in this scenario, the general told everybody to attack, but when they talked to their colleagues, what they found out is, so this guy told, you know, the malicious one to attack, but he said, well, I heard retreat. Okay, and he also tells the other guy, I heard retreat. So he's giving false information out, and so this is what an insane or a malicious lieutenant might do. Okay, and in the case of a malicious general, is he's telling different things to different people. Okay, does everybody understand the constraints? Okay, it's fairly simple, and the question is, how many insane folks can you deal with? And there's some impossibility results that are in that paper I gave you that kind of show that 3 is not enough. So if you have a general and 2 lieutenants, basically there's no way for the good lieutenant to do anything useful if one of the lieutenants the other lieutenant is malicious, because notice we have this scenario where the malicious lieutenant says retreat, the general says attack, and the lieutenant that's not malicious doesn't really have enough information to make a decision. And the same thing is true if the general says attack and retreat, then it turns out that you got 2 very confused lieutenants. Okay, so 3 players in this game is insufficient. And you could show that 4 players is sufficient. And in general, there's a way to basically turn this 3-player example into 3n or 3m players and basically prove this result, that you need to have the total number of players is greater than 3 times the number of malicious players. Okay? Or another way to say this is that the number of malicious players is less than a third. Okay? Question? Yes?
Why isn't it sufficient to just have the general sign the request?
So if you actually allow signatures, then you can start to do a little bit more. So what we're assuming here is this is without signatures for the moment.
Why would you do that?
Say again?
Why is it useful to do that?
Well, because the problem with signatures is that then requires you to have a signature infrastructure, which you can have under some circumstances. But this is basically the general version of the problem without putting signatures in play. And there are other, with signatures you can do slightly better. Questions? Okay, so lots of algorithms exist to solve this problem. And so the original one that's up on the website actually had a number of players, or a number of messages that were exchanged that had to be exponential in n. So it's kind of like, I heard, my one hop information I heard, the 2 hop information I heard, the 3 hop informations I heard, and so on. So it's basically 1 party, 2 party, 3 party, 4 party, n party messages required to solve this in the original case, and that's where we got exponential. It turns out there are newer algorithms that came up in about a decade ago from folks at MIT that have a complexity that's more n squared in the number of messages, which is a much more reasonable number. And there's a very good algorithm from Castro and Liskov that we even implemented in OceanStor at one point that's pretty reasonable. Okay? And this is all... so you could imagine calling this the Byzantine general problem is really Byzantine fault tolerance. And so they basically called this a Byzantine fault tolerance algorithm. And what you can imagine doing with this is actually getting it out of sort of this warrior framework and thinking about it in terms of distributed decisions, where a request comes in and you have a bunch of nodes that are all going to collaborate together to come up with the result, and they're going to come up with a distributed decision. So again, think about the lieutenant constraint we said before, which is all the non-malicious lieutenants are all going to come up with the same decision. And in the case in which the general is not malicious, then they will come up with the same decision as the general. Question?
Yeah, so in the general case, for the malicious players to cause a wrong decision, do they have to be able to communicate with each other? Or
The assumption is that malicious players have arbitrary resources, so they could communicate with each other at any.
do they know which other players are malicious?
They can potentially know which other players are malicious as well. They can do anything they want. And so we need to guard against whatever. And it turns out these protocols, it doesn't matter what the malicious players do as long as they're less than a third of the total players, that the rest of them can still come up with a distributed decision, which is kind of a cool result. Okay? Now, how did we use this? Well, for instance, in a distributed file system, what we did was the request might be something like, I'd like to commit this data. And the decision would be a yes or no on the commit. And if enough players properly decided to commit, then it would be committed in a way that was guaranteed to be reconstructible and a good decision. And so you can actually ask these players, the lieutenants, to do something like check access control, is this right consistent with other rights, and so on, and make a distributed decision, and then decide to vote, basically, to do that and do the commit. So it's basically a commit, no commit, rather than an attack, retreat decision. Okay? Questions?
So if your nodes aren't all doing the same thing, then inherently you have like one at the same.
Say again?
Like if your nodes aren't all, if it's not homogeneous, like if they're all
Right.
doing different things, then you inherently have like one at the same general, right? Because the yes or no.
So your question is sort of, do these have to be all identical or not? Or how do you pick the... So usually these protocols are dealt with, in fact, where all n players are treated identically. And at any one time, one of them has been voted as a general. And the other ones can recognize when the general goes insane because the protocol doesn't converge after a number of steps. And at that point, the ones that are still sane go and they re-vote and come up with a new general. And so part of the way this scheme works is it actually votes out a bad general rather than trying to deal with a bad general. And so the exponential part comes into play when you want to deal with a bad general rather than voting them out. So I think I may have also put this Castro and Liskov paper up. It's a pretty simple read if you're used to reading systems papers, and you can kind of see how this thing works. It's probably not on, it might be on the reading list on the lecture page, but it's certainly on the handouts page. Okay, so this is actually practical algorithm, and people do use this. The n squared is still a little bit large in number of messages, so you have to be careful what you commit using this, but it's practical. And you can see, by the way, can everybody see why you might want to do a distributed protocol using Byzantine fault tolerance? What's the equivalent of an insane player? Yeah. Yeah, compromised, virus, whatever. Okay. Now, before we finish this topic, suppose that one node has been compromised. What does that tell you about the other nodes' potential for compromise? Could be high, right? Because if they're all identical, then maybe somebody found out a way to break into them and they haven't done it yet. So the only way to really fix that is whenever you run into a problem, basically what you're doing is continuously reinstalling the software. So most of the protocols that use Byzantine fault tolerance in the most simple fashion have a very simple OS that keeps getting reinstalled over and over again to try to get ahead of the virus breakers in. And two, people talk about what's called n-version software, where you try to actually make sure they're not all identical, so the attack vectors don't mean that one that's broken into is easy to break into the other ones. But that starts getting tricky. Okay. So let's switch. So unless there are any other questions on Byzantine general, we're going to switch topics now into some more normal distributed topics. Okay. So remote procedure call. So this is going to be motivated by the fact that if you actually tried to build a messaging protocol by yourself, which you all are trying to build, right, with number 4 here, project 4, it's pretty low level to be constructing messages, sending them off, tearing them apart, interpreting them, at either side. It's a lot of work. And what you're doing for project 4 is fairly simple. Okay, so the folks that came up with remote procedure calls in general were trying to make distributed messaging easier to use. Okay, and what they did was they said, let's make something that looks like a procedure call as far as the programmer is concerned, but in fact sends messages. And that's called a remote procedure call. And what it does is it calls a procedure on a remote machine. That's why it's called a remote procedure call. And so then, as far as the programmer is concerned, they do they make a procedure call, and they get a result back. And so the code you write is all it's doing is making procedure calls. The fact that under the covers that procedure call is really getting turned into a message, sent to a server, executed on the server, turned back into a message, sent back, and then returned as a return from a procedure call is something you don't actually have to worry about as the programmer. Okay, so it's a very simple way to build up complex protocols. And so the client, for instance, here might do something like this. Call the method remote file system read on rutabaga, and it's translated automatically into a call on the server, file sys read rutabaga. So the fact that you called this on the client and it called this on the server automatically is supposed to be somewhat transparent to the user. Okay? So how do we do this? Well, obviously there are messages involved because we're talking to a remote server. Okay? So that goes without saying. On the client side, we typically have what's called a stub. So the idea behind a stub is it's actually a procedure like this remote file system read, but that procedure doesn't do any of the bulk of the procedure. All it does is it marshals this argument into a special format for the network. It sends the message off. It takes the response back and then returns it. So the stub fakes there being a procedure on the local side and calls a procedure on the remote side. And so what those of you that are familiar with the linking process, right, what you're actually linking against is you're linking against the stub on the client side. Okay? The server side also has a stub which you've linked against, and what that stub does is it takes messages that come in, which are procedure calls from the client, turns them into procedure calls, which call the server, takes the response, turns it back into a message, and sends it back to the client. So there's a stub on both sides. Okay, and so how do we make remote procedure call easy for programmers is we come up with a very simple way of turning a procedure call syntax into stubs so that we don't have to do that by hand. Okay? Questions? All right, is everybody with me? So the goal here is to make this as transparent to the programmer as possible. And this notion of marshalling, I just wanted to get some terms out. How many people have heard the term marshalling before? Okay, a number of you. So this is basically taking values that you're going to send to some remote machine, turning them into a canonical form of some sort, serializing them into bytes, etc. Okay, so it's basically taking the data you want to send in a message, it's putting it into the message in form of bytes, sending it off. Now, marshalling usually involves worrying about, for instance, is the ordering of integers on the client and the server the same? Okay, because you might have a client that has little endian integers and a server that has big endian integers. And if you have that, then if you're not careful, you have to switch them around. Okay? Everybody with me on that? So let's take a look at a typical RPC. So on machine A, which is our client, okay, it's going to call a procedure, which actually ends up calling the stub. The stub is going to take the arguments and marshal them into a network standard format. It's going to send it to a part of the OS that's handling packets. The packets are going to go across the network to a mailbox, which is the handler on the other side. The handler is going to send the packet into the receive stub. The stub's going to unbundle the arguments, turn it into a real procedure call, which calls the server. The server is going to take the response. It's going to return a response, which the server stub's going to bundle, send that back to the packet handler. Okay, it's going to send the response back to a second mailbox, which is then going to cause a receive message into the client stub, which is going to unbundle the arguments that were returned, return it from the procedure call, and now the client gets its procedure call. Question? Yes?
How do you deal with something that's not like functional?
So you can't. So this is purely functional. It's purely about a remote procedure call. Now, it's not functional in the sense of no state. The word functional is sort of overloaded. You probably ran into that in 61A in various ways. What this means is it's all about calling functions or procedures. Okay? So state can be kept on both sides, but if you need to send state from one to the other, then that would be part of a procedure you'd call at the beginning to set up the state. Okay? So what are some details? So there's an equivalence with the regular procedure call mechanism. So parameters are request messages, results are reply messages. The name of the procedure is passed in the request message. The return address is a mailbox, okay? So these are kind of equivalences. The stub generator is kind of the interesting part, which is a compiler that generates the stubs for you. And the way you do that is a programmer typically describes the argument in a special language called an interface definition language, which contains, among other things, the argument types and what return arguments are and so on. So as a programmer, if you're going to use RPC, typically you end up describing your procedures in this language. And then it basically compiles stubs for you and produces them on both sides. Okay. And, of course, there's cross-platform issues in how the marshalling goes that have to make sure that the stubs deal with message ordering. All right. Actually, let's take a brief break. I'll be right back. Excuse me a sec. All right, sorry about that. So among other things, as I mentioned, part of what the stubs do is convert to and from standard representations. So does anybody know, by the way, what the standard network order is for integers? Yeah, it's big endian. Very good. But it also has to potentially deal with things like different floating point formats or, different date formats. I mean, there's a lot of things potentially it might have to deal with. So are there any questions on that part? Since you got to think about this a long time. Okay. So how does the client know which mbox to send to? I mean, you're making a remote procedure call. How does it know where to go to for the server? Any thoughts? Yeah.
Needs to be configured beforehand.
Okay, so we might have to configure it beforehand. That's a possibility, sure. So you need to basically translate something like the name of the remote service into a network endpoint. Okay, that hopefully sounds familiar. So in general, we talk about this notion of binding, which is the process of converting some user visible name, like the name of the file server, into a network endpoint, which, by the way, is just another way of talking about naming at the network level. But it tends to be called binding in network parlance. And there's kind of a couple of possibilities here. We could do it statically, where when you link your client code, it has the IP address statically in it. Okay, or we could have dynamic, where what actually happens is we take a name and we go to some name server and use that to translate it into the mailbox. So which one do you think is a better idea? Okay, why is dynamic a better idea? Yeah.
Because if it's static, and if it changes, you're going to have to respond.
Yeah, so while static seems like it might be a plausible idea, it really is not very flexible. And so dynamic is pretty much the common way of doing things. And most RPC systems actually have a special server, which is not just DNS, but rather a server set up for the actual RPC technology you're using to turn the name of a service into an actual mbox number. Okay, question, yes?
Could you kind of view DNS just as like a specialized binding service?
Yeah, DNS is a type of binding service. Sure, I'll buy that. In fact, usually with a socket, you talk about binding an address to the socket. That's actually terminology that's used.
There are also things like, kind of like the mail system is in DNS, right? Isn't that kind of like, sort of like an RPC?
Yeah, I mean, there's a lot of things you could view in RPC form, although RPC in its purest form is really like you're linking a procedure. But yeah, you could view the mail system as getting that direction. Now, the question might be, how is this type of RPC binding more than DNS? That might be another question. And the way it's more than is it basically is turning a service into a mailbox, which could be not just the server name, but also ports on the server, or maybe even there are different services with the same port but a different internal name. So there's a lot of places where a lot of information we might need in order to have the service working. And why dynamic binding? Well, there's at least two reasons. One is access control. So the thing doing the binding can actually make a decision that you don't really have access and not even tell you the name. Another one is failover. So when the IP, if the server fails, you can just move it to a different server and change the binding in the local RPC name service, and nobody has to know the difference. Okay. So what if there's more than one server? Well, could give you flexibility of binding time. So it's possible that what happens is you actually give a different mailbox out to everybody who requests naming decision. Okay? And by doing that, you could make sure that unloaded servers get loaded and that overloaded servers don't get further overloaded. There's another way that you can do this, which is something that big places like Google and Yahoo often do under the covers, which is you actually provide indirection at the router level into the server. And so the main name service is actually giving the same mailbox to everybody, but when the requests make it to the endpoint, there's some other box there that decides how to forward them off to different servers internally. Okay, and this is actually what Google does in many instances. Okay, and why would you do it at this level? Well, this gives you more flexibility for the person providing the service to control how things are forwarded to different boxes. And now the other thing that you have to think about is, what if there's multiple clients involved? Obviously, the whole point of having a service is so that more than one client can use it. Well, that means that the return that comes back has to be directed to the right client. And so part of the outgoing message is often which return mailbox the response ought to go to so it gets back to the right client. Okay? Good. Any questions? Now, so what are some problems? So this idea seems simple enough. Well, one of the problems is your failures are now non-atomic. What do I mean by this? Well, it used to be that you had something running on your computer, the computer crashes, everything's dead. Now, when you have RPC involved, it's possible that you're using services from a lot of different servers, and now some of them might fail and not all of them, and now you got this kind of non-atomic problem where some things might have happened and others haven't, and you have to make sure that your state is not going to run into problems as a result. And distributed systems in general have more complicated failure modes than non-distributed systems. Hopefully that's obvious. So, you know, a user-level bug might cause an address space to crash. Machine failure, kernel bug may cause all the processes on the machine to fail. Malicious compromises, etc. I mean, there's lots of ways in which one party out of a multi-party transaction can be failing. And before RPC, the whole system would crash and die, and you'd be good because you can't make any progress. After RPC, you know, one machine crashes and you get partial progress. And I don't know what's worse, no progress or partial progress. Because in some cases, the partial progress, you have to go in and sort out the mess afterwards. Okay? So, and this is, you know, once you get an inconsistent view of the world, that's when you start coming into distributed transactions, and Byzantine commit is a way to make sure that everybody who is participating comes up with a consistent view of things. And so this is kind of popping back a level to two-phase commit, three-phase commit, Byzantine commit are ways of sort of making sure that these inconsistencies don't lead to globally inconsistent state. And of course, performance. RPC can't possibly be totally transparent to a user, right, because of performance, because the cost of an actual local procedure call is very, very much faster than using RPC to a service on the local machine, which is very, very much faster than RPC to the network. Does that make sense to everybody? Now, somebody tell me what I mean by same machine RPC. Why the heck would you ever do that? What's the point? Okay, communication between different processes on the same machine. Yeah. Why not? Right? This is another clean way of communicating between processes rather than having to set up shared memory between them. Okay? Somebody give me another reason why this might be interesting to do something sometimes on the same machine and sometimes on a network version. Yeah. Right. So it's possible, if something is overloaded, to migrate a service that was local to a remote thing, and you know, you've got more flexibility as a system manager. Okay, so that's kind of a cool idea. But it does mean that programmers potentially that are using RPC need to realize that there could be vast speed differences based on how it's being used, and it may be that they need to make sure, for instance, they do everything in a non-blocking fashion, or they have extra threads to do the RPC so that the rest of their system isn't held up while an RPC is happening. Okay, so as a programmer, you may want to be aware that this RPC is going to take longer than a procedure call. Okay? Good. So, now, as was brought up here, we can put RPC in sort of the pantheon of ways that we communicate between address spaces. Okay, we had shared memory, we had file systems, we had pipes, which, by the way, are Unix sockets. Okay, communicating to each other. That's how a pipe works. And remote procedure call is yet another way to communicate between address spaces. So RPCs can be on the same machine or the local machine, and examples of RPC systems you've probably heard many times. Corba. Okay? DCOM is probably one you've run into if you use Windows at all. RMI is Java's version. And what this is these are complete systems for letting you invoke procedure calls remotely on servers, and all of these systems include a binding service as part of them. And so usually if you install Corba or DCOM, there is a binding service of some sort associated with it. Okay? Like Windows has the domain controller, for instance, is often used, although there's, I think there's actually a separate naming service you can use as well. Okay. So I wanted to bring back microkernels before we close out RPC, because RPC is a crucial part of how microkernels work. So if you remember, the monolithic structure that we've talked about most this term is everything in the kernel is pretty much running at system level, and applications are the things running at user level. Okay, that's kind of what we've been talking about. The alternative here for a microkernel structure is actually that there's very little in the kernel, just some stuff that can handle the virtual memory, schedule threads, and handle RPC. And then everything else, even things like the file system, the windowing system, networking, all that stuff that you typically think of as being in the kernel is actually running at user level. And the way you communicate with things is via RPC. Okay, so you're an application, you want to open a file, you're actually going to do RPC to the file system. Okay, or you want to display something on a window, you're going to do RPC to the windowing system. Okay? And so you can see why it's called a microkernel, by the way, because this is micro compared to that, I guess, is the way. Yeah, question?
File system application is allowed to export physical disk. Why can't the app just access that directly?
Because that's a great question. So if the file system can access the physical disk, why can't everybody else access the physical disk? And the answer is protection. So basically, the access of the disk is going to be mediated by mapping the disk into user space only on this one process and not the other ones.
So the microkernel is still aware of like file system. The file system is hard coded as being a special application, and the Windows is hard coded as a special application.
Yeah, I would say it a little differently than that they're special applications. What I would say is that these particular user processes have resources that the microkernel grants them. Okay? And nobody else is allowed to have them. Yeah. So why do we do this? Well, fault isolation is a big one. So you could imagine that the file system could crash and the rest of the system might survive. Now, of course, you have to think a little bit about what it means to lose the root file system on a Unix-like variant. It's probably not particularly pleasant. So file system crashing and everything going on as if nothing happened is unlikely to happen. But the hope here is that then the file system could restart and everything would be good. Okay? It certainly enforces modularity because you're required to go through a very well-defined RPC interface. And it's location transparent because we could take the file system, which may be overloaded from one machine, and just move it to another machine, and the RPC could be redirected to another machine. So we can actually take services that were normally stuck kind of inside of one big monolithic kernel, and we can now start moving them to different machines based on load. Okay, so it actually does give you a lot more flexibility from that standpoint. Okay, questions? Good. Okay, so Administrivia. So we had extension to tonight on the design doc, as you're probably all well aware. Design reviews are Monday, Tuesday after Thanksgiving, and hopefully we have all the design reviews up, right? So you guys should sign up if you haven't. And the final project code, by the way, is due 12/7, so that's in the RRR week. It's like Tuesday. Okay. Final is coming up, and it's in 10 Evans. It's from 8 a.m. to 11 a.m., and you need a dumb calculator, so it's something with no network connection. I know that's hard to believe that such things exist, but I'm sure they do. And 2 sheets of notes, both sides. And the final lecture, you have until tomorrow to send me topics. I've got several now, so I will collate these and talk about them on Monday as to what people asked for. But if you have anything that you've been burning to ask for in the final lecture, make sure to send it to me tomorrow, because Friday I'm going to go through and put things together. Okay? I won't be doing it on Thursday. That much I can guarantee. Hopefully I'll be eating a lot of turkey. Okay. Any administrivia questions? No? Okay. So let's switch gears now one last time to kind of our final sort of topic of the day is distributed file systems. And let's talk a little bit about what that is. I mean, in principle, it's very simple. You've got clients that are using the network to talk to servers, which have data. Okay, so the client doesn't actually store the data is stored remotely. And of course, this is completely common. You're all very familiar with this. You have data on remote servers, and you probably don't even think about it much. But the data you're using when you use such a client machine is actually not stored on the client. It's stored remotely. And the question that we want to talk about today is kind of how does that work? And basically, the notion is transparent access to files on the remote disk in a way that you don't have to be aware that they're remote other than perhaps a performance issue. And one of the things that always comes up is naming. So how do you name files that are on a remote server? Well, the obvious thing you could do is you could name files as a host name : local name pair. Okay, so every time I want to talk about a file, I have to say COEUS, which is our file server, /user/ /Kubatron/ whatever. Okay, this doesn't sound particularly good, right? Because the moment your files have to change from COEUS or some other file system, you can't migrate anymore, and now your file names are sort of obsolete. What you're probably much more familiar with is this notion of mounting. And I want to show you the Unix version. So mounting basically takes this location-dependent name and it buries it in the file system in a way that you don't have to worry about. So for instance, here is a typical tree of files in a Unix system: /user/ Jane / prog whatever gets me a file. But what's kind of interesting is it's possible that what I've done here is only /user Sue / users Jane are actually local, and I've done a mount operation of COEUS : /Sue into the Sue subdirectory here. This is something that you have to do as system level typically. You have to have root privileges. But once you've done that, now I can just use names like /user/ Sue / bar, and I'll end up transparently picking a file that's off on some server because I've mounted it into the file system. Okay, so it's now become transparent to the user once the mount has happened. Okay, and here's another example where I've actually mounted Kubi : /Jane here, and then this subtree is now on the Kubi file server, but down here I've mounted Kubi : /prog there. So when I traverse the file system, I'm actually into /prog on the Kubi server once I've down in here. That make sense to everybody? Question? Yes?
The nested mount, that is a mount on the remote file, is that correct?
You know, it isn't. What happens is you mount the remote file system to this point, and now the local file system kind of knows about this tree. And so this mount, the second mount, is really only local. So the remote file system doesn't know anything about you having mounted locally here. It's purely local state. And you could kind of think of, the way to think of this is that what we really are trying to do when we resolve a path name is, remember, when we talked only about local file systems, we sort of resolve from inode to inode. We start at root, and then we work our way through. Well, once you've added mount into the picture, all that really has to happen is the thing that's resolving the path name needs to at some point know that it's resolving names somewhere else. And it does that by sort of looking at prefixes of names. And so it doesn't have to actually mount something on the remote server to do this.
If your remote server decides to add a file to your mount point, what's going to happen?
So if it adds a file in here,
Well, so it's normally your mount point has to be in the directory, right?
no. Oh, you mean underneath here?
Right.
So once you've mounted, so suppose there was something in the /Jane directory here, locally before I did the mount. Once I've done a mount, it's completely covered up. And the remote server doesn't have any control over that.
Okay, so maybe I'm misunderstanding. We've got probe directory, which is a mount point located in the middle of the Jane directory switch.
Yep.
So the Jane server, and they happen to be both Jane and Switch, which is maybe part of the issue. The Jane directory structure today exists on a remote server.
Yep.
The probe directory is a empty directory on that remote server.
Doesn't have to be empty. It could have all sorts of stuff in it, but the moment I mount something else on top of it, I'm getting the other new thing, not what's there. Okay? Good. So a final thing that might be interesting, as you can imagine, is that every file is in a single global address space. Has a unique name no matter where it's actually stored, and there's some global naming service that turns a name into a location for us and helps us get at the files. And so that would mean that rather than accessing things through a series of mount points, every file actually has a unique name that I just use. Okay? And surprisingly enough, there's a file system which I'm going to talk about in the context of caching in a moment called AFS, where in principle every file that was in the AFS world was in a had a well-defined name. Okay, it had a unique name. No matter where you were in the world, it had a unique AFS name. So that actually has some nice advantages to it, as long as you can move files around from physical server to physical server while still keeping the unique name. And that had some way of doing that. Okay. In the peer-to-peer world, which we may talk a bit about in our final lecture, what this actually translated to was that every file had a unique 160 or 256-bit hash that described it, and then you put them in a namespace that would translate names into that hash, and that would be global regardless of where the data was actually stored. So we'll talk a little bit about that when we get into peer-to-peer systems. Okay. So how do we do these remote file systems? Well, there's something called the Virtual File System, VFS, layer, which is really was developed originally by Sun Microsystems for NFS. And what it does is instead of inodes, it has what are called vnodes, virtual nodes. And the vnodes are unique across a whole bunch of file systems. So remember, inodes are only unique within a given file system, whereas vnodes are unique across file systems. And the vnode layer allows you to mount both local things and remote things into a global system, well, into a local system, on the local node, such that the normal interfaces like open, read, write, all of those system calls work. They automatically figure out kind of which file system to go to and route the request to the proper file system. So this is a way of taking multiple local and remote file systems, integrating them together in a way that is transparent to the user. Okay? And same system call interface that you had before, it just can potentially be remote. Okay? So that system call interface I'm talking about, open, close, read, write, seek, okay, all of those. So this was developed, by the way, for NFS originally. So the VFS layer had NFS in it as the very first instance of a virtual file system. Today, VFS is pretty much in anything you might use, because these type of file systems can be disks, they can be USB keys, they can be remote network drives, etc. So let's take a brief look at the simplest version of a distributed file system now, which would be client sends an RPC like read to the server returns data. Okay? Client says write, server returns ACK. Caching, if there is any, is purely at the server side. So this is just the buffer cache we talked about when we talked about file systems. Now, is this a good system or a bad system? What could you say about this particular simple idea? Fast, slow, complicated, simple? Okay, slow. I'm hearing slow. Why slow? So you may not, well, but presumably this read RPC says exactly what data I want. So go ahead, you were going to say something. No.
I was wondering how well it's scaled much.
So if you have many clients talking to the server, it might not scale well because the server get overloaded. I'll buy that. Yes.
What if we want caching on the client side as well?
So one of the things that seems to be bad about this is there's no caching on the client side. And so if you happen to repeat a request, then you always have to go across the network. Yeah.
One nice feature, though, is because there's no caching, you don't get inconsistent data.
Yeah, so the nice feature about this is no caching means no inconsistent data. 6 of one, half a dozen of the other, right? So the other thing that I will point out is this RPC interface is, or as I like to say, 6.5 of one, half a baker's dozen of the other. But anyway. So the RPC interface makes it particularly simple to implement as well, right? Because all I have to do is I turn a read into a read on the local file system of the server. So you can see that by using RPC, we've sort of made this partitioning really simple. We just sort of, we come up with our IDL description. And when the RPC shows up, the server here does the system calls. It takes the data and sends it back. And we just have stubs on both sides. And poof, we've got a distributed file system. Simple. OK? So the idea here is purely a remote disk. We're using RPC to basically give us remote procedure calls. There's no caching. The advantage is it's completely consistent and simple. Disadvantage is performance. OK? Going over the network much slower than going to local memory. Lots of network traffic. It's not really well pipelined. Server can be a bottleneck. Lots of problems with this simple version. Okay, so let's take about a 3-minute break, and then we'll come back and we'll make this better by putting caching in. All right. So let's actually put a cache in the picture and see what happens. So what we're going to do here is use caching to try to reduce the network load. So we can put caches on both the clients, and we already had one in the server side. And basically, in practice, what we're going to do is actually use the buffer cache, which we talked about both on the client side and on the server side. And the advantage is that if you can somehow open, read, write, close, whatever, and it stays purely within the client's cache, then you don't need any network traffic. So that's much faster. Okay? So here, we do read, sends out an RPC, looks up some data. Data comes back, gets put in the server's cache because it's part of just the file system, and it gets returned to the client's cache, and the read result is returned. Let's say it's V1. Now, successive read does the same thing very rapidly because it just goes in the cache. And another read. Okay? Now, some problems that we can encounter with this is failure. So for instance, suppose that all we do is write, and it goes to the local cache, and then what happens? Well, suppose the client crashes. Okay, so now what we just did is we just lost data because the only good copy was in the cache. So what do we have to do to fix this? So we could try to keep a local log. Okay, what else could we do? Yeah. So we could try to get it, somehow if we can get the data on the server, hopefully the server is more reliable than your client. So that might be a take, right? So for instance, if we make sure that writes go straight through to the server, now they're in the server's cache, and maybe it's less likely to crash. Or for instance, the server might be more likely to have RAID or some way of holding on to data. Okay, and it'll send an ACK back, and we'll be good. And if we do that, we make sure the write goes all the way to the server, then a crash of the client is no longer bad, except for the person trying to use the client. But you come back up, the data is still good. Okay. Another problem, of course, is cache consistency. So take a look at this scenario I've got here. We read F1 into this cache, and then we wrote F1 on this cache, and now the two caches are not consistent. And so the problem here is that a read here is going to return V1, and a read here is going to return V2. Okay, just because the two caches are inconsistent. Okay, so what do we have to do to fix this? Yeah.
Could we implement something like how caches don't normal time systems that when we write, then the server sends out some sort of message to validate.
So what you'd like to do is what we said hardware caches do, which is you write here and you get an invalidate sent back to the other side. Okay, that's actually a potentially good but slightly more sophisticated example than we're going to do for NFS. We'll get to that when we get to AFS, but that's a good answer. Hold on to that thought. So what else could we do if we're not going to, so let me just back up for a second. The biggest problem with this idea of hunting down caches is that then the server needs to know about all the clients and every data item that they've got, and so that's more overhead. Okay, so is there a way that we can do this without the server having to hold on to all that information? Yes? Yeah, so the client could ask if the data has changed or not, right? Okay. So, and we'll talk about a couple of options for this in a moment. So, what if the server crashes? Well, if the server crashes, can the client wait until it comes up and then just keep going without knowing any difference? Okay, so what is the consequence of a server crash? Could lose data. So let's put that one. Let's assume that doesn't happen. What else could happen?
If you have inconsistent caches, it seems like it'd be real hard to figure out which one.
So if the server crashes, we might no longer be able to know which caches are consistent or not. Okay, I'll buy that. What else? Yeah. Why? If you try to read more data, it won't work anymore. Why would that be? Okay, so the server crash prevents you from doing something, but let's talk about it coming back up again. So the server comes back up again. Yes?
Maybe there was stream of packets that were in the middle of transmission, but then the server crashed in the middle. Like only some of them got sent.
So we could end up with some of things being sent and not everything. Yeah. How about state? What if there's state shared between the client and the server? Is there any simple instances of that you could imagine? Do you remember the seek system call? What does seek do? Open, seek, read. Yeah, go ahead.
Change your position in the file.
Yeah, so it changes the position in the file. So that sounds like that could be state at the server if we're not careful, right? Yes?
Why would you destroy that client side and send it with each request?
So you could try to remove that state at the server if you somehow sent it in every request. Okay, I'll buy that. So my point in this discussion here is there may be, if we're not careful, state that the server loses when it crashes, and we've got to make sure that that doesn't get in our way if we want the server to be able to crash and come back up. Okay? That might be a solution. So any data in server memory but not on the disk can be lost when it crashes. Shared state across RPCs can be lost. Okay? Here's another one you probably didn't think about. What about message retries? So you originally sent a remove message to the server, and you didn't get an ACK or something. So then you send it again. Now, what's the consequence of the server seeing RM foo twice? Well, it sees it the first time, does it, but the client doesn't think it got that message, and then it gets it the second time, and now it says, well, there's no file, error. Okay? So we actually potentially have non-idempotent operations we have to be careful about if the server fails as well. NFS does a little bit of an ad hoc thing, which in the process of retransmission, if you get a remove twice and the second one doesn't find the file, it assumes it's okay. But that's kind of a fine print sort of in the protocol that you have to think of, right? You have to be a little bit careful about these things. So NFS actually developed a stateless protocol where what that means is there is no state ever shared between the client and the server. Okay, and the motivation with that was then the server could crash and come back up and the client could just keep going and nothing bad happens, assuming no data was lost. Okay, and so NFS is a good example of a stateless protocol. And for instance, in a stateless protocol, since there's no state shared, we got to do things like send the seek pointer on every read. Okay, because the server doesn't have any state. In fact, it doesn't even know which files are open and closed, because that would be state. Okay, so instead, all of our requests to the server have to be of the form, read this block or write this block, basically without it knowing whether we went to the trouble of opening the file or not. Okay, and if the client crashes, we could lose our modified data in the client, and we talked about one possibility there is to force all the writes to the disk, to the server. So here's NFS, and NFS was one of the first protocols like this. The VFS layer, the original layer, was developed by Sun Microsystems for the NFS file system. And here the client makes system calls which go through the VFS interface, which properly get directed to the NFS client, which goes through an RPC layer. XDR, by the way, is the extended data representation, which was Sun's IDL, interface description language, which is a network-independent format for things like integers and so on. Goes across the network. There's an RPC stub on the other side. Goes to the local NFS server through the VFS interface to the local file system and to the disk. Whew. Lots of pieces, but they're all kind of decomposable, right? The VFS layer gives you uniformity interface to the client. The NFS client and server side are really just doing RPC between each other. And this VFS layer is talking to a local file system. Question? Yes?
A lot of features in NFS.
A lot of what?
Just to people complain about unstable or have problems. Which part of this is a couple of points that you want to set up?
Well, NFS, stability issues with NFS kind of come of two forms. One is the server's crashing or something like that. The other is cache coherence issues, and I'll show you in a moment where those can arise. So those are kind of two types of problems. And it's just, NFS is a complex system like any other, and it's got its sets of bugs. The other thing I will point out is NFS can run over either UDP or TCP. UDP is very fast if you're on a local, if you're in the local area, but potentially if things get lost, then it gets a little unstable, and so there's some issues there too. So 3 layers for the NFS system. As I mentioned, there's the Unix file system interface, which talks to VFS and things like open, read, write, close, etc. The VFS layer distinguishes local from remote files. And the NFS service layer is really this bottom layer that uses RPC to communicate. And the protocol is, well-defined RPC for file operations. It's got things for reading or searching directories, for manipulating links in directories, for accessing file attributes, reading and writing files, etc. The crucial thing here is that the two sides of the NFS protocol never share state. It's always the case that a client sends all the information needed to do the access in every message. And the other thing that the original NFS sort of forced was write-through caching, which means that every time you do a write, you're not actually allowed to return to the client until that write has been guaranteed to be on the server. So basically, you go to do a write system call, it goes through all the layers across the network, gets an ACK, comes back up, and then you return to the client. So as you can imagine, that means that writing individual data can be very slow on NFS if you're not careful. Okay. Upside of that is data is safe on the server. Downside, pretty slow, especially in an environment where not a lot is being lost. And so subsequent versions of NFS, past 1, basically allowed you to put it in a mode where it didn't do write-through caching on everything, but now you have the danger that the data might be on the client when it crashes, but not yet on the server. So you get kind of speed and pipelining for a little less reliability on your data. Okay. So stateless protocol, as I mentioned, every request provides all the arguments. So for instance, a read might be sort of read at, here's the inode number, here's the position, not read some file handle. You don't have to open or close because there is no open or close. Every operation in NFS is idempotent, so you can perform it multiple times and the right thing happens. The slight thing that you have to be careful with is, for instance, remove operations. You have to deal with the fact that they can't be retried quite properly. Okay? So read and write file blocks, for instance, are particularly idempotent. Can do them over and over again. And we talked about remove. So failure model was originally transparent to the client. So if the server crashes, the client stalls. And then the server comes back, the client just keeps going. That was the model. Is that a good idea? Is making things completely transparent to the client so it never knows that the server crashed a good thing? How many people think that, yes, it's a good thing? Okay, one of you. How many people think that, no, it's not a good thing? Okay. How many people think that it depends on circumstances? Okay. So, it's kind of interesting. Originally, NFS was pretty much targeted at a mode which was hang until the server comes back up. And this was supposed to be completely transparent to the user, but it's never a file or a server crash is never transparent to the user, right? You know that things crashed. And what was bad about this is the server would crash and it'd be down for a long time. And if you did a PSAUX and you actually looked at what processes were there were a whole bunch of processes hung up in disk weight with a little D by them, and you couldn't even kill them. The only way to get rid of them was to reboot the processes that were stuck waiting on NFS. So that particular mode was not very desirable. And so most NFS users now mount it in what's called a soft mount, which is a case where when the server goes down, you just get an error back from your read or write, and so then your processes are not hard locked in a disk weight state. Okay. So what about cache consistency? So NFS has a weekly consistent system. Basically, client polls the server periodically to check for changes. So the polls happen once every 3 to 30 seconds. And if the file is changed, then the server will tell you it's changed. So here in this case, with this inconsistency we mentioned earlier, what happens here is client says, is F1 still OK? The server says no. You get an updated cache, and you're good to go. OK? And of course, if multiple clients are writing to the same file, what happens then? OK, well, first of all, you're going to start to see inconsistencies. But you could kind of ask yourself, sort of, what sort of cache coherence might we expect if more than one client is writing the same file? Good consistency or bad consistency? Or unpredictable? How many people think it's unpredictable? Yeah, it's unpredictable. So for instance, here, got client 1 is reading. Suppose the file starts out with contents A. Client 1's reading and it's getting A. Client 2 is reading. But then client 1 starts writing B. And at some point, client 2 might get some of A and some of B. And then it starts writing C. And then client 3 might get parts of B or C. And client 1 might get parts of B or C. So the problem is, NFS is a block-based interface. And if multiple people are writing, you can get completely inconsistent and interleaved results.
Couldn't the server just put like a conditional variable or something so that you never interleave your operations? You're only getting one.
So it's an interesting thought to try to put some sort of conditional, you're thinking about a lock or something so that you don't get inconsistent results. The problem is the server is not allowed to have any state. So it gets really hard to do something about this, right? And what might you actually want? Well, if we wanted the distributed system to behave as if all processes are running on a single system, we'd like it to be the case that if a read finishes before the write starts, we always get the old copy. Right? If the read finishes before the write starts, you always get the old copy. If the read starts after the write finishes, you always get the new copy. And otherwise, you get either old or new. So that would be what a local system view would be. Okay, so if you think about your local file system, it's really not all that much better than this. So another problem with NFS, though, is that if the read starts more than 30 seconds after the write, you get the new copy. Otherwise, you're not sure you'll get the new copy. Why is that? Well, because your cache is only checking for updated data periodically. Okay, so this is where you start to get some weirdness with NFS. If you know what to look for, under some circumstances, you can actually see your writes not entirely there, and then they show up. Okay, and this was particularly bad for older versions of NFS. They've made it better over the years. I remember I used to have one machine I was editing with Emacs, and then I'd go to another machine that had more power to do a make. And if I did that too fast, the make would break because it was getting sort of half of my changes I just saved out from my Emacs buffer, not the whole thing. Okay, and so newer versions of NFS are much better than that. But the pros and cons of NFS, pros are simple, highly portable. You can get NFS pretty much on anything today. Cons, sometimes inconsistent. And this polling is really unscalable. If you have 1,000 clients and they're all polling the server, you're swamping the server doing nothing but looking to see whether caches have updated. Okay? And this is really a problem with having no state. Forcing the server to have no state causes us to poll, which causes a lot of traffic. Okay? Now, we're running low on time, but I want to tell you about an alternative, which is the Andrew file system. This has been around for a long time. It does have state. Okay, and the basic idea is it allows clients to register callbacks so that the server keeps track of who has copies of what file. And on changes, the server immediately tells everybody who has an old copy to invalidate their old copy. Okay, so the plus here is because we have state in the server, we don't have to poll. Okay. Another thing that Andrew file system does that's very cool is it has semantics called write through on close. What this means is that changes are never propagated to the server until you do close. So if you do open, write, close, it doesn't matter if somebody else is opened in the middle of you doing writes. They're always going to get the old data. It's going to be a nice, consistent old data until the moment you hit close, and then everybody from that point on that doesn't open will get the new data. Okay, so this says that you always get a completely consistent copy. So these are pretty nice semantics. And it turns out with these semantics, you can do caching in a much better way. So for instance, AFS would cache using the local disk. You would have complete copies of the files that you've opened, and you could read and write them locally until you close the file, and then it would send all the changes over. And so it actually would allow you to have a much bigger cache than would fit in your memory. You could actually have the cache be on disk. And so AFS actually had complete copies of big chunks of the file system on your local disk. And so that was pretty nice from a performance standpoint. So when you open, if the file's not on the local disk, then you go get it from the file server and set up a callback with the server. On write, you basically send the copy to the server. Okay? If the server crashes, this is unfortunate. Now you've lost all your callback state, at which point it actually has to talk to every client it knows about and says, hello, do you have state? And so what we've done is by adding state, we've made the normal mode operation a lot cheaper because there's not a lot of polling. But now after a crash, it takes us longer to get back up to speed where we have to get our state back. Okay? And by and large, relative to NFS, it's a lot less server load. The disk is a huge cache. More files can be cached. Callbacks are nice because the server is not involved with any read-only files. So basically, AFS was a much better improvement over NFS. Unfortunately, it hasn't really made it as widespread as NFS. And I think part of this is because AFS was spawned off into a company with IBM. They formed something called DFS, so it was technically proprietary, and then it didn't get implemented in all operating systems, and it's out there, but it's really not that prevalent. Question? Yes?
Yes. So why exactly is it the server doesn't do something like construct a log when on server crash that you just not want to see the log?
Yeah, I think probably it does do that, but it's got to verify it a little bit and so on. But yeah, you're right. With some logging, you could make the reconstruction process less painful. I'd buy that. Question? Yes?
So for a client that has a diskless setup where it actually mounts a remote file system,
Yes.
AFS would work.
Well, in that case, with a diskless file system, I think there's a version that you can do of AFS where it only caches in memory. So what you'd do is you'd make a memory disk or a RAM disk, and then you could cache in that. All right, so let's say in conclusion and let you guys get off for the holiday. We talked about the Byzantine generals problem, which basically says 1 general, n-1 lieutenants, and as long as you have basically less than a third of your servers are malicious, then you could make a good decision. And this is actually a pretty cool property. I encourage you guys to read the paper. It's kind of amusing. Remote procedure call is basically another way of doing network communication, which is a very smooth, simple interface we're all familiar with, which is procedure calls, and it's a way of turning procedure calls into network traffic automatically. We talked about the virtual file layer, which is a way of making local and remote file systems all together under one roof. We talked about distributed file system ideas, and in particular, we talked about cache consistency in both NFS and AFS. And anytime you put caches into the picture, consistency is always an issue, and it's a question of what the best way to handle it. All right, I think I'm going to say Happy Thanksgiving. See you guys on Monday. By the way, there's no midterm on Monday, in case you didn't get the memo.